This video will cover an adaptation of Ben Eater's binary to decimal algorithm for the Z80 CPU. First, there will be a quick review of the algorithm, then a look at the code that I have written, and finally a look at the code running in an emulator. This video assumes you have an understanding of the divide by 10 algorithm. If you are not familiar with the algorithm, look at Ben Eater's excellent video linked below in the description. I also assume that maybe you have looked at some Z80 code but are not at an advanced or expert level. I am certainly not at an advanced or expert level myself. Here's a recap of the algorithm. First, store the number we want to convert to decimal in the right-hand side of a 32-bit workspace. Then there are two nested loops. The outer loop iterates for each decimal digit in the given binary number, and an inner loop for each of the 16 bits in the given input number. In each iteration of the inner loop, shift the 32-bit workspace 1 bit left, then subtract 10 from the left 2 bytes of the workspace. If the carry flag is set, store the result of the subtraction back into the left 16 bits of the workspace. Back in the outer loop, the remainder of the division operation is now in the 16 left bits of the workspace. This is stored as decimal digit result. The remainder is cleared from the 16 left bits of the workspace, and the workspace is shifted left an extra time. There is a check for the outer loop end condition where the 16 right-hand bits of the workspace are all zeros. If all of these are zeros, the outer loop ends, else proceed with another iteration of the outer loop. And at the end of both of these loops, output the results. There is a difference with the subtraction operation to how Ben Eater described it and how the Z80 subtract operations behave. I will explain this when we get to the subtract operation part of my code. Now let's look at some Z80 code. So, first step is to create a new file. I'm going to call it binary to decimal.asm. And just to be clear, I will be copying and pasting code that I've already debugged prior to making the video. First thing is a comment to remind me what this file is about. Next are some platform dependent values for addresses of the stack and the memory that will be used for the workspace and storing of the result. The values here are for my homebrew Z80 computer. You will need to change these for the system that you want to run this code on. Next, I add a macro to add the A register to the HL register. Z80 does not provide any instructions to add 8-bit numbers to 16-bit numbers, so several steps are needed. I will use this macro a couple of times later on. Then the origin statement. Again, this is platform dependent. Change the origin of this code to your needs. Then set up the stack register, and the BC register will hold the number to convert to decimal. Next, I will create the outline of the algorithm with some call commands and the inner and outer loop, and I will put in the functions later. The first two steps are to set up the workspace memory and result space memory. Then a label for the outer loop. I need to make sure the carry flag is cleared. Z80 doesn't have an instruction for clearing the carry flag, but ORing A with itself has no effect on the A register but does clear the carry flag. The C register will be the counter for the inner loop. Do not worry, I am not overwriting my given digit. The setup workspace function will store it safely. Then a label for the inner loop. Then a call to a function to shift the workspace left 1 bit. And a call to a function to subtract 10 from the left 2 bits of the workspace. And a conditional call to a function to store the subtraction result if the carry flag is set. Then decrement C and a conditional jump to complete the inner loop. The inner loop is effectively one round of divide by 10. Therefore, at this point, the left 2 bytes of the workspace are the remainder of the division, and therefore the first decimal digit. 4 more steps are needed for the outer loop. We need to store the remainder from the division, as this is the decimal digit we want. The remainder needs to be cleared from the workspace, and the workspace needs to be shifted left an additional time. And then a test for the end condition of the outer loop, where the 2 right-hand bits of the workspace are both 0. And then a conditional jump to complete the outer loop, a call to a function to output the result, and an infinite loop to end the program. This is now the outline of the algorithm. Now for the 9 functions that I'm calling. The setup workspace function is easy. It puts the address of the workspace in the HL register and puts 0 in the first 2 bytes of memory and the given number in the second 2 bytes. On an emulator, it may not be necessary to put the zeros, but on actual hardware, I don't want to make any assumptions about the state of any particular memory address. The setup result space function is even more trivial. I need to keep account of how many decimal digits are found, so I set first byte of the result space to 0. I am using the exclusive OR A command here to set the A register to 0, because it takes less memory and fewer clock cycles than the load A0 instruction. Note that exclusive OR A does affect flags, but that does not matter here. Next is the shift left function. I set HL to the address of the right-hand byte of the workspace by taking the start address and adding 3. Then I have a small loop for each of the 4 bytes, using the B register to count. RL stands for rotate left, and bracket HL means this command works on the byte at the address in the HL register. As well as rotating a byte left 1 bit, RL puts the current value of the carry flag into bit 0 and the former bit 7 as a new value for the carry flag. Then HL is decremented. Note that the 16-bit versions of decrement and increment do not affect any flags. And then a DJ and Z to complete the loop, and return. Next is the subtract 10 function. This necessitates a discussion about the difference between bin-eater's subtraction step and Z80's subtraction behavior. So far, I've talked about a 32-bit workspace comprising of 2 16-bit words. But the workspace is actually 33 bits because it uses a carry flag as well. This discussion of subtraction will focus on the right-hand 16 bits and the carry flag. In bin-eater's algorithm, the carry flag is set to 1 before subtraction, and is used as a bit to borrow from if it is needed. For example, subtracting 10 from 13, the carry flag would remain at 1, and subtracting 10 from 8 would clear the carry flag. But Z80 subtract instructions work differently. I will use the SBC HLDE instruction for the step, which subtracts DE and the carry flag from HL. So, the first difference is that the carry flag needs to be cleared before the subtract instruction to get the correct subtraction result. The second difference is after the SBC command, the carry flag acts as a borrow or underflow indicator. In the case where DE is larger than HL, the carry flag will be set. If DE is smaller or equal to HL, the carry flag will not be set. This means that after the subtract command, the carry flag is the opposite of what it needs to be for the algorithm. Therefore, the carry flag needs inverting after the subtraction command. Now, back to the code. I load HL with the workspace address again. I want to load DE register with the first 2 bytes of the workspace, but there is no load bracket HL command, so 3 instructions are needed. I load HL with 10 for the other operand of the subtraction. Now DE and HL are in the wrong order, so I swap the DE and HL registers. Then the subtract command, invert the carry flag, and return. Then the keep result function. The subtraction result is still in the HL register, which I need again for the workspace address. So I swap the HL and DE registers again, load the HL with workspace address, and copy the subtraction result there. The store remainder function will use the 8-bit versions of increment, add, and subtract commands, which will overwrite the carry flag. To preserve the carry flag, I use the rotate left B command, which puts the carry flag value in bit 0 of the B register. I load HL with the address of the result space. I increase the count of their decimal digits. I load A register with the count of decimal digits. I add A to HL using the macro defined earlier. HL now has the address to store the decimal digit. RRB is the reverse of RLB and restores the carry flag. I load DE register with the workspace address. The decimal digit is in the second byte of the workspace, so I increment DE. I load A register with the address in DE, and load the address in HL from the A register, and return. The clear remainder function is trivial and follows the pattern I've used so far. The test end function needs to compare 2 bytes of the workspace to 0. This will overwrite the carry flag, so like before, I rotate B register left to preserve the carry flag. This time, I use the IX register for the workspace address, exclusive OR to clear the A register, and then I OR the A register with the 2 right-hand bytes of the workspace. The OR command sets the 0 flag, so if after both OR commands the 0 flag is set, the 2 bytes in the workspace are both at 0. However, I cannot use the RRB command to restore the carry flag, as this overwrites the 0 flag. But the RRA command, which has a space in it, can rotate right without affecting the 0 flag. So I load A register with the B register, I rotate A right to restore the carry flag, and return. Finally, the output result function. This is obviously very platform dependent, but the main thing is that the decimal digits are stored in reverse order, so the display loop needs to account for this. I load HL with the result space address. The first byte of the result memory is the decimal digit count, so I load A with the count, and also load B register with a count to use as a counter in a loop. I add A to HL, and HL now has the address of the most significant decimal digit. Then the output loop. I load A with the decimal digit, add 48 to convert to ASCII. I output the character. You will need to change this command to whatever is needed for your system. Decrement HL and complete the loop. And return. Phew. That is all the code. I already know it works, so let's look at it running in an emulator/debugger. This is my very crude emulator based on libz80x. At the top, in white, is an address, and just below that is the instruction that has just been executed. Then, in blue, are the state of the registers. Then, in purple, the state of the 0 and carry flags. In yellow are the 4 bytes of workspace memory with their values in binary and hexadecimal. And in green, the 6 bytes of result memory with their values in decimal. So, first, the setup instructions. Load the stack pointer, load BC, initialize workspace memory, and result space memory, and then set up for the inner loop. I'll step into the shift left function. Note that in the case of 2-byte instructions, the instruction appears for both addresses and the registers and memory are only updated on the second byte of the instruction. Most of the rotate instructions and instructions involving the IX register are 2-bit commands. And stepping into the subtract 10 function, the carry flag is not set, so the keep result function will not be called on this iteration. Decrement C and jump if not 0 at the end of an inner loop iteration. A quick look at the second iteration of the inner loop. Now jumping directly to the end of each iteration of the inner loop, back in the outer loop, the functions to store the result and to clear it from the workspace. I'll step into the test end function, and now stepping across iterations of the outer loop. The decimal result is now found. So, stepping into the output result function, showing the correct output order. And the end. Future possibilities include code optimization, adaptation for 8-bit, 32-bit and signed numbers, and adaptation into a generalized division routine. This is the end of the video. I have made a couple of mistakes. Did you spot them? Thank you for watching.